Hey, welcome back. And so now we're going to look at the scalar or Cartesian equation of a plane. Now, let's remember how nice Mr. White is that if you don't remember what a term means on your test, so if I ask you for the scalar or Cartesian equation and you say, sir, which one is that again? Yeah, I'm not going to be very helpful at all. So here's the scalar equation of a plane. It's ax plus by plus cz plus d equals 0, where a, b, and c is a vector normal to the plane. So this is similar to what we were doing with lines. Consider the two scalar equations. One for 1x plus 2y plus 3z plus 4 equals 0. And consider the next one, 2x plus 4y plus 6z plus 8 equals 0. These are complete scalar multiples of each other. Complete, everything. That means, guess what, guys? They're the same plane. Okay, so let's not get too confused on stuff. If we can reduce each and every term, then it's the same plane. If just one of them doesn't reduce, then no, it's a different plane. Okay, so here's a question. Determine the scalar equation for the plane with the vector equations. I think we can do that. We know that the formula is, for the Cartesian equation, is ax plus by plus cz plus d equals 0, where the normal of the plane is equal to a, b, c. So guess what? Go find a normal. How are we going to do that? Well, I've got two direction vectors. Take two direction vectors that are in the plane, and we're going to take their cross. Now, correct me if I'm wrong, audience. Is this not the exact same one that I took the cross of earlier? Yeah. Okay. So just for fun, let's do this. So for normal, let's do 2, 0, negative 1, 2, 0, negative 1. And just for giggles, let's do 6, 2, and 0. So I didn't reduce it this time. Didn't happen to notice it. Too bad, so sad. Here's my normal. It's going to be 0, subtract negative 2, so it's going to be 2. It's going to be negative 6, subtract 0, so it's negative 6. It's going to be 4, subtract 0, so it's going to be 4. There's my normal. Since the only part of the normal I really care about is its direction, I can reduce that to 1, negative 3, 2. Is that the same answer we had before, audience? Yay! So it works. So this is going to be my a value. This is going to be my v value. This is going to be my c value. So we're going to sub into this equation. So it's going to be x minus 3y plus 2z plus 2z plus d equals 0. My pen doesn't seem to be flowing as well as it should be. Oh no, we might need ink. We'll fix that at the next pause. So we'll move on to an alternate pen. Do I like this pen? Yeah, it's not bad. All right, so this is what we have. So what are we going to do? What are we going to do? We know the we know the normal. What we don't know is this d value. But this d value is dependent upon a point. It would be dependent upon any point that's in the plane. Do we know a point on the plane? The answer is a resounding yes. We know a point on the plane. That's a point. Now, guys, these are not points. Don't be putting them in for x, y, and z. That's a big no-no. Those are direction vectors. That's a point on the plane. By the way, if they give you a lot of points, only the points on the plane will work. So don't be confused by that. I'm going to do that to you. There'll be more points to choose from. You have to get the point that's actually on the plane. So in this case, it's going to be 3 minus 3, 0, plus 2 times 2 plus d equals 0. 3 subtract 0 plus 4 is 7. D equals negative 7. So the equation of the plane is going to be x minus 3y plus 2z minus 7 equals 0. Da 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 da! You have the scalar equation of the plane. And here's the secret. It's unique. Everybody that does this question will get the same answer, or they'll be wrong. Isn't that cool? That's cool. So do I need to write something here? Do I need to say sub in any point on the plane? Maybe. I did it anyway. There you go. All right. That's me out of here. And we'll do the next one.